Good day, students. So welcome to number 8 on our proof by mathematical induction. And don't forget that we have a wide variety of math tutorials on mathgotserved.com. All right, so before we go ahead and start with the problem, let's go ahead and write down the plan of attack to summarize the steps that we're going to go through to execute our proof by induction. Okay, so plan of attack, we can break it down into 3 parts. Part number 1 is known as the base case. All right, base case. For the base case, we're just basically going to show that the statement is true for n equals the first natural number that satisfies the equation. Okay, so let's say n equals 1 is the smallest natural number that satisfies the equation. Then that's what we'll do. That is what our base case will be. And then for part 2, in our plan, we're going to have to do something called the inductive hypothesis. We're going to make an assumption that will basically be a basis for the next step. Okay, so inductive hypothesis, we're just going to assume that the statement is true for some arbitrary k. In this problem, since k is already going to be part of the problem, I'm going to assume assume that the statement n equals, how about we use m? N equals m is true. Okay, for some m in the set of natural numbers. And then last but not the least, we have to do something called the inductive step. Inductive step is based off of our inductive hypothesis. Okay, so assuming that our inductive hypothesis is true, does that follow that the next step is also true? All right, so for the inductive step, we're going to show that n equals m is true, implies that or follows that n equals the next step m plus 1 is also true. This is the hardest part. In most cases of a proof by mathematical induction, this is the part that involves most effort. Okay. All right. So after doing that, then you can conclude by mathematical induction that the statement is true. All right. So let's take a look at the problem. Let's just call this number 8. So for number 8, let's see. Prove that the discrete sum from k equals 1 of k squared, from k equals 1 to n of k squared is equal to 1 over 6 n times n plus 1 times 2n plus 1. All right? All right, so let's start with part 1. Part 1 is our base case. Base case. So let's see, what are we going to do in our base case? We want to show that, let's see, n equals 1 is true. All right, the statement is true for n equals 1. So k is basically our indexing system. K is going to be taking on values of different integers, different natural numbers from 1 all the way to n. All right. So part of the problem is for, let's not forget that, for all n in the set of natural numbers. Okay, so let's go ahead and carry out our base case. So all we're just going to do is plug in 1 into k. So since that was the first number, we're not adding it with any other number. Okay, so if we plug in 1 there, then we're going to have, well, let's write out the statement first. K squared equals 1 over 6 n times n plus 1 times 2n plus 1. So if I plug in 1 here, when k equals 1, we're going to have 1 squared. Is it equal to, question mark, we don't know yet, 1 over 6, plug in 1 here also, 1 times 1 plus 1 times 2 times 1 plus 1. Okay, 1 squared is just 1, and on the right side we have 1/6. Let's see, this is 1 times 2, and then this is 2 times 1, 2 plus 1, 3. right? Is 1 equal this simplified value of this arithmetic expression? Well, let's see, this is going to be 1. Is 1 equal 1 over 6? 2 times 3 is 6, right? So this cancels out. We just have 1. Actually divides out. And then is 1 equal 1? The answer is yes. So what does that mean? Our base case or the foundation of our mathematical statement is sound. Now that we've done our base case, let's go ahead and move to part 2 or step 2, which is the inductive hypothesis. Inductive hypothesis. All right, so for the inductive hypothesis, we're going to assume that n equals m is true. All right, you notice why I didn't use, on my other proofs I used n equals k, but in this problem k is already taken. All right, so you don't want to have a situation where you're using a variable that's already taken. It can result in confusion. So I selected a different letter, which is m. Okay, so assume that n equals m is true. So how do we make that assumption? Let's go ahead and write that down. We're going to assume that the discrete sum from k equals 1 to n of k squared is equal to, well, actually, we're going from k equals 1 all the way to m, not n anymore. We're going to replace our n with m, okay? Because notice here we have n equals m. So anywhere we see anywhere we see n, we'll replace it with m, okay? All right, so on the right side, let's go back to the problem so I don't make mistakes. So all these places you have n, so we're going to replace them with m. So on the left side, replace that with m, 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 m. Okay, so let's go ahead and apply that change. So we're going to have 1 over 6 times m times m plus 1 times 2m plus 1. So we're going to assume that this statement is true for some m in this set of natural numbers. Okay? Alright, so this is our inductive hypothesis. Now, part 3 is our inductive step. Inductive step. Alright, so for our inductive step, we want to show show that if n equals m is true, that follows or implies that n equals m plus 1 is also true. All right? So by mathematical induction, we have this pattern repeating like a domino for all natural numbers. Okay? Now, before we do that, let's think about n equals m plus 1. How is that going to look like? We're just basically going to replace, everywhere we see m, we replace it with m plus 1, okay? So that will be on the left side of the equation. The goal is, I'll show you what the goal is in a minute, but on the left side of the equation, I'm going to plug in, I'm going to start with the sum, discrete sum from k equals 1 all the way to what? M plus 1, because we're taking a step up of k squared. Now, what is this equal to? Is the question. What is this entire expression equal to? Well, just to make sure you understand what's going on with this sigma notation, I'm going to rewrite this sum in a way that makes it obvious, and then I'll condense it back for you, okay? So what this expression is asking you to do is you take in all the integers or natural numbers from 1 to m plus 1, and you're squaring them and adding the sum of their squares, okay? So starting from 1, you plug in 1 there. So you have k. K is basically 1, 2, 3 plus, I'm sorry, 1, 2, 3, all the way to m, and then m plus 1. Okay, this is just scratch work. You don't have to write this down. So what we're going to be doing is we're going to be taking all these values of k and plugging them into this expression, k squared, and then we're going to sum the result of the squares. Okay, so what does that look like? We're going to have, if you plug in 1, you have 1 square. So sigma says you add it to the next index, evaluated at this expression, 2 square plus 3 square plus da 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 plus m square plus m plus 1 square. Put this in parentheses. So that is what this nice little sigma notation is telling us to do. All right, so this sigma expression is a condensed form of this entire expression here. So we're going from k equals 1 to m plus 1. Now what I want to do is I want to break it apart. I want to extract the sum all the way to m. So if I extract the sum all the way to m, I'm going to have the sum from k equals 1 to m of k squared. Now what did I do? I just stopped right here. This is where I stopped. I stopped right here. What's left is this expression evaluated at the upper limit of our discrete sum, which is m plus 1. So m plus 1 squared must be added here. So plus m plus 1 squared. So in order to carry out this substitution or this rewrite of this expression, you really have to understand what's going on with this discrete sum. All right, so these two are exactly the same thing. Now we're going to go ahead and try to make it look like this expression in our inductive hypothesis, but we want all the m's to be m plus 1, m plus 1, m plus 1. Now this is a little bit difficult to accomplish if we do not know exactly what our end result looks like. So what I'm going to do is I'm going to work backwards a little bit. I'm going to cheat technically. I'm going to start with the end and simplify my end results to a form that's easy for me to arrive at working from this expression here. All right. So let's write down what our target is. Our target is, I'm going to put it down here so as we get closer we can know what we're doing. This is scratch work, okay? So this is my target. This is what I want my final expression to be. 1 over 6, instead of m, I want that to be m plus 1, okay? And then the next one, instead of m plus 1, I want it to be m plus 1 plus 1, okay? And then the last one, instead of 2m plus 1, I want this m to be m plus 1, okay? So it's going to be 2 times m plus 1 plus 1. So the goal is I want to simplify this expression or manipulate this expression in such a way that I end up with this result. You see, that's not quite easy to arrive at, right? So how about I simplify this a little bit more so I have a target that's easier to arrive at, okay? So let's simplify this a little bit more. So this has 1 over 6 times m plus 1 times m plus 2. And then you distribute this 2, and then you have 2m. When you distribute this 2 to 1, you have 2 times 1, which is 2, plus this 1 here, which is 3. Okay, 2m plus 3. Bam. Okay, this looks easier to work towards. Okay, so the whole idea, or the key takeaway here is, if your end result is very complicated, you want to work backwards a little bit, work from the end towards the answer a little bit, and then start from the beginning and work towards a much more practical end result. Okay? So if I were working blindly, there's no way I'm going to end up with this. Well, I could, but it's very difficult. So this would be my target. And then from this setup right here, I know for a certainty that this ends up to that. So this is our end result. And we want to start from here and end up here. Okay? So I'm going to just leave this down here just to guide me. Now, let's go back to our proof. Can I make use of my inductive hypothesis in this statement? The answer is yes. For my inductive hypothesis, I assume that this expression is equal to that. So this expression shows up here again. So using our inductive hypothesis, I'm going to make a substitution. I'm going to substitute this with what we assume it to be equal to in our inductive hypothesis in step 2. So this is going to be equal to 1 over 6 times m plus 1 times 2m plus 1 plus m plus 1 quantity square. Okay, this is based on my assumption in 2, which is our inductive hypothesis. All right. Okay, so this is good. Now this is our end result right here. Keep an eye on the target so we can know how to work this out. You notice that 1, 6 and n plus 1 are factors. So what I want to do is I want to factor out 1, 6 and n plus 1 from these two quantities right here. It's obvious that n plus 1 is present, but there isn't any, 1, 6 here. But I can factor any number I want from any number. It shouldn't be a problem. Just it might not look pretty, but it can be done. So let me rewrite this in such a way that it's easy to factor out 1, 6 n plus 1. So I'll leave this alone as 1, 6 m times n plus 1 times 2n plus 1 plus, there's a 1 here, right? The multiplicative identity. Now I want to rewrite 1 with a denominator of 6. That shouldn't be hard. I can write it as 6 over 6. 6 over 6 is 1, right? The goal is I want the denominators to match, so that's how I write it. And then this is n plus 1 times n plus 1. So the beauty of this rewrite is it makes it possible for me to factor out 1/6 and n plus 1. All right, so let's go ahead and do that. If I factor out 1/6 and n plus 1, I'm going to have 1/6 m plus 1. If that is factored out, I'm left with m. Let's put it this way. I'm left with m times 2m plus 1 plus, now if I factor out 1/6 from 6 over 6, I'm just going to be left with 6, right? 6 times n plus 1, like that. If you want to check your work, you can distribute it back. You end up with that expression right there. Okay, so now that that has been factored out, we can now focus on simplifying this expression down here. All right, so let's go ahead and do that. Also, we don't want to lose sight of our destination, right? We're going on a complicated journey here, and it's good to have our target in our within our view so we know how to manipulate this expression. So it's looking good right now. We have the 1/6 m plus 1 piece right there. So hopefully we can simplify this expression to become n plus 2, sorry, times 2m plus 3. So let's go ahead and do that. So we have 1/6 times m plus 1. And then over here you distribute the m, and then you have 2m squared plus m plus, distribute the 6m plus 6. Okay, and then this becomes 1/6 times m plus 1 times 2m squared plus 7m plus 6. And then we have a quadratic trinomial here. Let's factor that by grouping. So make an x, tiny little x here. I'm going to use the AC method. So AC is 12 and B is 7. Two numbers that multiply to give you 12 and add to give you 7, 4 and 3. Let's put that in here. So we have 1/6 m plus 1 times 2m squared. Replace 7m with these two numbers, plus 4m plus 3m plus 6. All right, so let's go ahead and factor by grouping. Let's see, break this up right here. And then we have 1/6 times m plus 1. And then factor out the GCF from these two. We have, what do we have? 2m times m plus 2. And then factor out a 3 out of here. 3 times m plus 2. Like that, looking good. And then it factors out into 1/6 m plus 1 times, and then you combine these two together after factoring out m plus 2. So let's factor out m plus 2. So if we factor out m plus 2, we have m plus 2 times 2m plus 3. All right, that's great because it looks exactly like this piece. And I will know for a certainty that this simplifies to that because we just did that right here. Okay, so let's go ahead and finish this up. So we're simply going to write, this becomes 1/6 times m plus 1 times m plus 2 is the same thing as m plus 1 plus 1. So I want to use the right grouping symbol here. So we're going to have quantity m plus 1, and then 2m plus 3 can be written as clearly as 2 times m plus 1 plus 1. Boom. And that's exactly what we wanted. Okay? So let's erase our target. We've already arrived at it. We don't need it anymore. So let's make our concluding remark. So we just simply say, since the statement is true for our base case, n equals 1, and truth for n equals m, implied that n equals m plus 1 is also true. The statement is true by mathematical induction. By mathematical induction. All right? So that's that. You put down your box of accomplishments to indicate that you have concluded your proof. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to our channel. And do post a comment to let us know what you think about this presentation. We really appreciate it. More clips can be found on mathgotserved.com under the pre-calc section under Induction. Thanks again for watching and have a wonderful day.